So this is Dr. Kavita Singh, Associate Professor in Department of Civil Engineering in Institute of Aeronautical Engineering. So today our topic will be for discussion is about satellite resolutions. So in the previous lectures we have just discussed about the different types of satellites and different types of Indian remote sensing satellites, types of orbits, SWATs, and various types of satellites we have seen in the previous lecture. So in today's lecture, we'll just know about the resolutions of satellite imagery. So basically, the satellite should have resolutions for capturing the information. So let us see what type of resolutions a satellite is having at the time of the capturing the information. So before we enter to this topic, just let us go through the contents. What are the contents we are going to discuss today? So we have to discuss about first about what about resolutions. What is resolutions? Types of resolutions, pixel and digital number, IFOV, that is instantaneous field of view, and spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. So these are the contents we are going to discuss about satellite resolutions in this topic. So let us start with this resolutions. What does the resolution mean? So resolution refers to the smallest size an object or detail can be represented in the image. Smallest size in sense. When we talk about resolution of an image, that means we are talking about the pixels. What a image is having, a digital image is having number of pixels. Combined with the number of pixels, it has a image formation, and the pixels will be having lot of pixels here. So as we see the number of pixels are closely spaced, the resolution will be more higher. So if the pixels are like this, then the resolution we see it will be higher. So if the pixels are very at the distance, it's not closely spaced like a distance of this much distance it has. So that means these are two types of digital data we generally call it. Suppose this is the digital data. Now in this digital data, this we have one type of resolution, this we have one type of resolution. So when we see to this digital data, this resolution is low resolution. Why? Because it is having less number of pixels which can be counted, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I can just count the number of pixels. That means if I am able to count the number of pixels, that means that satellite data is having very low resolution. So if a satellite image or a digital image is having many pixels, it has a many pixels here, like it may cover 1000 pixels, it may cover 2000 pixels. That means these kind of data will be good resolution. Okay, good resolution, or we can just call it as high resolution. So this data is having high resolution. Okay, so high resolution, and this data is low resolution. So resolution means it's like the smallest size which is visible in the image. Visible in the image. So detail can be, and the detail can be represented. For example, for a simple example, when you take a photo from a camera which is having a resolution of 2 megapixel, and if you take a photo from a camera which is having a resolution of 50 megapixel, that means 2 megapixel means it is having a less number of pixels, 50 megapixel means it is having more number of pixels. To 2 megapixel photo will be very low resolutions, the details will be represented very blurred, we are not able to see the image. When you see the high resolution photo which is having 50 megapixel, that means we are able to identify the smallest detail, smallest size in the object or detail in the image. So higher resolution means that pixel sizes are smaller, providing more detail. So for example, 30 centimeter resolution satellite imagery can capture details on the ground that are greater than or equal to 30 centimeter by 30 centimeter. So this 30 centimeter means the 30 centimeter object on the ground will be visible in this image. So here, for example, you can see there are three photos here. So this is the satellite image. This is the satellite image. Satellite image. Okay. So this satellite image, from this we have this small corner which is shown here in a bigger view. So the small corner is having the number of pixels here. So number of pixels you can see here, 1, 2, 3, 4, 5, 6, 7. So there are so many pixels over here. Like that, in the whole image there are number of pixels present over there. So how we can see this image? If the number of pixels are more, we can see the clarity and we can see the details in the image. Now this satellite image, so as I'm saying that it is having number of pixels. So each pixel is having number on it. Suppose this is pixel number 1, it is having a number like 170, 238, 85, 255, 221, 0. So there are different numbers which are given by the system to the pixels. So each number is having, it is called as digital numbers. So these numbers are by default, it is given by the system to the satellite image or any kind of digital image we can call. So wherever we see 0, 0, 0, 0, that means that represents the same type of feature over there. Like I can see here 0 here. So if we see here, that is a black color pixel here. Now if you see the 0 here, we can see a black color pixel here. Now if you see the 0 here, again you can see a black color pixel here. So same type of feature will be having same type of digital number over there. Now if you see 225, 255, 255 is one pixel number here. Now 255 is one pixel number here. So same pixel you can see here, 255, 255. So like this, the system will be having each pixel, by default it will give a number called as digital number. As we scan the image, as we take the photo, as the photo is converted to a digital form, as the data is converted to a digital form, immediately the system will be providing a digital number to each pixel of the image. So this is called as resolution. In terms of resolution, if we see a satellite image, we have to just see that the resolution should be a higher resolution so that we are able to identify or differentiate the different types of features in the image. Right. So basically, types of resolutions we have is like spatial, spectral, radiometric, temporal. This will be discussed in the coming slides. So resolution means the smallest objects which are the smallest detail which is represented in the image and it can be identified. Now types of resolution. When we talk about types of resolution, we are having spatial, and these are the sensor characteristics. So we have spatial resolution, spectral resolution, radiometric resolution, temporal resolution. Now we have pixel and digital number. How do you understand about the pixel and digital number? Just now I explained you about the pixel and digital number. So there will be a digital photo which is having a number of pixels over here. Number of pixels over here. So here it is having number of pixels. Okay, like this pixels will be there. So these pixels are called as digital numbers. We generally call it as DN numbers. So a typical image derived from sensor consists of small equal areas, refers to a picture elements or pixel arranged in a regular row and columns. Each pixel has a numerical value called as digital number that records the intensity of electromagnetic energy measured for the area ground represented by the pixel. So the DN range from 0 to some higher number on a grayscale. Each pixel is also give x and y coordinates to place it. The image can be therefore be described in a strictly numeric terms or on a 3 coordinate system with x and y locating the pixel and z giving the DN displayed as a grayscale intensity value. So this is how it looks like in a larger form if we see. So this is our image. Here we have a pixel over here or area over here. Suppose if we take this area also, so same type of representation will show here and it will be having again in the form of digital numbers. So wherever it has 0, so that same kind of feature will be present. It has 38, same type of features will be present. If it has 136, same type of features will be present. So all depends based on the type of the feature. If it is showing as a pixel in the image, so that particular color will be having same type of DNM. We call it as digital. Now let us understand what is IFOV. That is instantaneous field of view. Instantaneous field of view. That means, suppose this is a detector. Detector means it's like our satellite, and our satellite is having a sensor over here. So sensor will be having a optical view. Sensor will be having a optical view. Optical view means from this point how much area is covered. So like that we have in the photogrammetry also. So if you have an aeroplane here and it has a lens over here, camera over here. So how much area the camera can see? It's like a eye. This eye, how much area it can be captured, is called as instantaneous fields of view. IFOV. Okay. So most commonly used measure for spatial resolution for any sensor based on the geometric properties of the imaging system is instantaneous field of view of a sensor. So IFOV is defined as the area on the ground that is viewed by an instrument from a given altitude at at any given instant of time. So instant of time means exactly at that same point, same time, exactly how much area the sensor has been captured. So sensor will capture the information, or sensor or optical system or camera, we can say how much area it may capture. Suppose here it is capturing like this, so it may capture this much area also. That depends on the sensor resolution again. Now for greater clarity of spatial resolution of any remote sensing imagery, it is more appropriate to introduce the term pixel or picture element. So one pixel on a digital satellite imagery represents an instantaneous field of view on the ground. Each IFOV is filed by the digital number. Okay, and on each digital number indicates some inherent property and the terrain element in the image. Now let us start with the spatial resolution. So here, when you talk about spatial resolution, so here just now we have discussed about pixels and the number of pixels present, and what is low resolution and high resolution. So in spatial resolution, when you talk about spatial resolution, that means it is in terms of scale. Okay. Generally, we in aerial photogrammetry we call it as scale, or any map we call it as scale. But when you talk about the satellite image, it's a resolution. Okay, spatial resolution specifies the pixel size of satellite images covering the Earth's surface. So high spatial resolution is 0.6 to 4 meters. Medium spatial resolution is 4 to 30 meters. Low spatial resolution is 30 to less than 1000 meters. Okay. Now, 0.6 to 4 meters means 0.6 to 4 meters on the ground. Suppose this is the ground. So whatever objects if we see which is of 0.6 meters or 4 meters, it will be visible in the image, and it is very high spatial resolution. So these kind of spatial resolutions are used in the infrastructure development, which help us to get the detailed information about the objects which are present on the Earth's surface. So medium spatial resolution is also helpful for the resource development, because the resolution will be 4 to 30. So if the resolution is 4, we are able to find out the infrastructure development, but if it is 30 meters, then we are able to map the resource information from this type of data. So low resolution is broadly classified in the ocean regions. It is not at all suitable for the infrastructure development. So broadly we can just see in the low resolution image. Now, spatial resolution of a sensor refers to the size of smallest possible features that can be detected. So this is like about the terms of scale, like terms of resolution. So more number of pixels you have, more higher spatial resolution. Okay, higher spatial resolution. Then less number of pixels we have. This is low spatial resolution. This is low spatial resolution. So spatial resolution of passive sensor depends primarily on their instantaneous field of view. That means how much area it has captured, and that too it depends on the passive sensors. Passive sensors means if like I hope you remember we have discussed in the previous lecture what there are two types of remote sensing, passive and active. So this passive and active we have two types of sensors, passive sensors and active sensors. So passive sensors when we talk about, that means it needs sunlight for the capturing the information. It needs sunlight for capturing the information. So when the sunlight is available, so it will capture the how much area it will view. That view is captured by this type of sensors. So IFOV is the angular cone of visibility of the sensor and determines the area on the Earth's surface which is seen from a given altitude at one particular moment in the time being. The size of the area viewed is determined by multiplying the IFOV by the distance from the ground to the sensor. So this area on the ground is called as resolution cell and determines the sensor's maximum spatial resolutions. So that all depends the number of pixels. See here in this picture we will be more, I mean it will be more clear to you to understand. Now we have three images here. So this is our aeroplane, okay, aeroplane or satellite, let us say. Okay, so it is having a instantaneous field of view. That means it is capturing this area. So from this area it has captured. Now we have a resolution of 80 meters here. 80 meters. Okay, and here we have 15 meters. And here we have 1 meter. So we have three different resolutions. Now, can you identify the difference between these three? Right? So I think we have discussed in the aerial photogrammetry also at the time of scale discussion. We have discussed like there are two types of scale, large scale and small scale, right? So when we talk about large scale, that means the area coverage will be always less. Okay. So when it is large scale, area coverage is less. Why? Because large scale will capture the information detailed. Okay, detailed information, but area coverage is less. So here if you just compare these three images, these are of same area. So one is 80 meter, 15 meter, 1 meter. So now in 80 meter we will see most of the area is covered, like large area is covered, right? When you talk about 1 meter, very less area is covered. That means 80 meters means it is instantaneous field of view. The distance from the camera is more. So it has captured, suppose here is the camera, it has captured the entire area like this. Okay. So when it captured more area, the details we can identify as less. So how much detail we can identify in this? Very broadly we can identify like there is a river over here. Okay, here is a river, and here we have some red color of vegetation, and here we have some blue color of settlement or residential areas. Now if we come to 15 meters, somewhat the area is reduced over here, right? Maybe we can say only this portion is captured, this portion is captured. Okay, so this area is only this much portion because it has 15 meter of resolution. That means it is having more higher scale than 80 meters, right? So it is having more higher scale than 80 meters. Now if we see, this area is less, and the details are more. Okay, details are more. How the details are more? You can see here, you can see the river, right? This is the residential areas we can see. vegetation part you can see, few of the roads you can see. So the details will be somewhat increased. Details will be increased, area will decrease. So this is the difference. 80 meters area is bigger, details we can see very less because the resolution will be very low. Low resolution. This is low resolution. Okay. So 15 meter is high resolution compared to 80. So this is high resolution. So if you are talking about high resolution, that means detail we can find out more. So if you zoom to this maximum level also, we are able to identify these details over here, right? Now if you talk about 1 meter of resolution, 1 meter of resolution means of this image, only this portion will be covered in this because it is only 1 meter. So here you can see the details here. Roads we can see very clearly. There is a tower here we can see very clearly. Buildings here we can see very clearly. Water body it's there very clearly. Here small buildings are there. So details is more, but the thing is area coverage is very less. So this is the higher resolution. 1 meter is the high resolution. 80 meter is low resolution. So when you want to find out the entire area with 1 meter, then we need to collect these all these type of tiles, this type of small grids, and then we have to merge it together to get a clarity of the image, right? Because here we cannot find the details. So I hope you understood. Spatial resolution is in terms of scale. When it is a large scale, then the resolution is high, but area coverage is less. Okay, large scale means this is the large scale. Here we can see area coverage is very less. We can't see here any kind of vegetation, we can't see here any kind of river in this image. But when you see this image, you are able to find out the vegetation, rivers, residential areas. But here you can just see only a corner of the image. In this on the corner of the image, we are able to find the details, but the area coverage is very less. Okay, this is the difference between spatial resolution of the image. So when we talk about spatial resolution of an image, when you want the satellite image for the infrastructure development, then we have to go for 1 meter of resolution. We cannot go with this 80 meter of resolution. So when you talk about 1 meter of resolution, then only we are able to get the information about this developmental activities, right? Now see here, it's more clear picture as I was discussing. So when you talk about 8 kilometer, as it is very low resolution, 8 kilometer. So the pixel will be only 1 pixel, only 1 pixel. Resolution is like this. That means we can't see the details in 8 kilometers. When you talk about 4 kilometers, the pixels will be like this. In 2 kilometers, again the pixels will be increased. So how much increased from here? 8 to 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pixels are increased compared to 8 to 2. So which one is the high resolution from here? Now 2 kilometer is the high resolution from 8, but not actually higher. Compared to 8, 2 is the higher. So here next we have 1 kilometer. 1 kilometer is having more number of pixels compared to 2 kilometers. Now 500 meters is having more number of pixels compared to 1 kilometer. Now 250 meters is having more number of pixels compared to 500 meters. So now if you see this 250 into 250 meters, so many pixels over here, you can't even count. So when you are unable to count the pixels, and you can identify few of the features here like this, some features we can identify in this image. Okay, but here also somewhat little bit. Here it is too blur, we are very hardly. Here we can't, here we can't, here we can't. So this is how the spatial resolution looks like. So in 80 kilometers or 8 kilometers of resolution, we can't work with the data. It is only broadly we can classify because the pixels will be very much less. When compared to 250 meters, the pixels will be more. That means 250 meters on the ground will be visible in the image. So 250 meters will not be visible in the 8 kilometers of the image. So that is the difference. So this is the high resolutions we have. High resolution. We have here low resolution. Okay. This is the difference here. Now let us see in this image. Now suppose 30 meters of house, 30 meters of pixels. Now 30 meters, if we, the output if we see, it will show only in 1 pixel. That means what is the detail in this? We can't identify. Now 5 meters means the output will be like this, like red and blue. That means somewhat we are able to identify there are some details present here. Now if you talk about 1 meter, total details same as it is, it will be showing as a display in this output. Okay. Now see here, we have here Landsat MSS satellite data, and this is year of 1975, and with the resolution of 100 meter into 100 meter grid. So this was the condition of the image, condition of the satellite data. Okay, that means in the year 1975 we are able to get the resolution of very low resolution. So this can be the resolution of the scale. You can see here 1:50,000 here. So it might be having 1 kilometer of resolution. Okay, so that means the clarity of the image is not there. What is this kind of image? We are unable to identify. Like we know, generally we know red color means vegetation, so we can stop that this is vegetation. And what about this all features? We are unable to identify. Now coming to the same picture we have in 1989 with a better resolutions. Now compared to this previous one, you see grids are improved in this in 1989. So somewhat we can see here is the water body, but still we are unable to identify because this is all grids are countable. We can just count the grids over here. Now next image in the 1997, the clarity has been improved. So here we can see it's a residential area. This is the residential area. This is the water body. This is the road of going over here. This is the water tank here. So some more details we are able to identify in the year 1997. This is of IRS 1C PAN plus list data. This is PAN plus list data. That means PAN data will be black and white. PAN data will be black and white. We call it as panchromatic. Panchromatic with a resolution of 2.5 meter or 5.8 meter. Okay, so this is how we see this data. So when you merge pan and list, we are able to get the output of this kind of data. Okay. Now this resolution, when you talk about in the year 2000, we have a Iconos satellite data in the year. Iconos, in the previous lecture also I told you what is Iconos image. So Iconos image is a very clear picture which gives the resolution with 1 meter of resolution. That means 1 meter object on the ground will be very clearly visible on the image. Now previous pictures you see very blurred. Now you see this image, the clarity, how clear it is. We can just see the buildings here. Small buildings also we can see. Top of the building we can see. This is the road we can see. There is a small channel going over here we can see. The small water body is here. Small buildings over here. So all details we can see here in this Iconos. So Iconos is a very good data, satellite data for infrastructure development. If you want to go for infrastructure development, you can go through this data. Now coming to the spectral resolution. What is spectral resolution? So a sensor spectral resolution specify the number of spectral bands. So these kind of resolution is the resolution which gives the information in different bands. So when we have studied about the electromagnetic spectrum, we have studied the different kinds of bands in that short wavelength region, long wavelength region, and visible region. So the spectral resolution means depending on the type of the object, the reflection of the image, reflection of the image, or absorbance. It will show us the how many bands it captures the information. So in this sensor can be collect reflected radiance, but the number of bands is not only important aspect spectral resolution. The position of band in the electromagnetic spectrum is important too. So now high spectral resolution, when you talk about high spectral resolution, that means it should have 220 bands. So when you talk about medium, 3 to 15 bands. Low spectral resolution, 3 bands. So high spectral resolution means it should just cover the 220 bands. Medium spectral resolution means it should cover the 3 to 15 bands. Low spectral resolution means it should cover 3 bands. And it has to give the information in the different bands. Now, when we see the spectral bands Landsat B1, B2, B, here we have Landsat images. So these are the images which gives us the information in band 1, band 2, band 3, band 4. So how many bands? 4 bands it is giving us the information. That means we are able to discriminate, we are able to differentiate the image even though if it is a black and white image. We are able to differentiate the image here, river, okay, and all this types of building we have here, different type of vegetation we have here. So how many bands it gives the color? It's like spectrum means how many colors the image is represented. Suppose we are able to see 3 and 4 colors. That means 3 color means only 3 band, 4 color means only 4 bands, 1 color means panchromatic, only single band. So these are all panchromatic images, okay, panchromatic. So it is giving band 1, band 1, only one band information. So if these images will become to a color image, it will give us in 4 band information. So band 1, band 2, band 3 and band 4. Like this, we have here bands 1, 2, 3, 4. So this is the target. So when the target is reflected by the sensor and by the object, and when the satellite captures, when it passes through the prism, it goes through the 4 bands of information. So this is multispectral remote sensing. Like this we can see here, we have false color image, we have true color image. True color image means actual image how it looks like. False color image means the wrong imagery. Wrong imagery in sense, now you see here vegetation is in green color, here vegetation is in red color here. This is called as false color, this is called as true color. So it gives us the information in 4 bands, 1 band, 2 band, 3 band and 4 band. Okay. Next, we have spectral response or spectral signatures. So, spectral response means we have discussed in the previous lectures also. Spectral reflectance curve means how many bands it reflects, absorbs. So, when you talk about vegetation, you start from 0.4 to 0.9 here. So, here is in 0.4, it is absorbing, it is going up in 0.5 to 0.6, again going down, again going up. So, it is having lot of reflection up and down configuration. So, that means it is giving the information in 0.4 band, 0.6 band, 7 band, 0.8 in 4 band information it is giving. Like that water is totally absorbing. So it is not giving much information. So that's the reason absorption will take place. That's the reason in the satellite image, the water body will be present in the black in color. Right? So vegetation always it will be red in color, while the maximum reflection of this vegetation will be in the IR region. IR region is infrared region. Okay, IR region. Next we have this IR region where that's our black body. Okay, like this it shows. So FCC means false color composite. Near infrared it looks like this, and red look like this. Okay. Spectral signatures we have already discussed in the previous lecture also. So this is the result of spectral resolution. Okay, result of spectral resolution in how many bands the satellite is providing us the information. Now if you see visible band, near infrared band, SWIR. Okay, so 3 bands it is giving us the information of clear water, soil, rocks and heavy vegetation. Now coming to the next resolution, that is radiometric resolution. So this is very important part again. Radiometric resolution is what? It is to discriminate or very slight differences in the energy. So radiometric resolution of an imaging system describes its ability to discriminate very slight differences in energy. That means energy in terms of electromagnetic energy when it falls on the ground surface, how easily we are able to differentiate the objects. Now we have here four images, 2-bit, 4-bit, 8-bit, 16-bit. So four images of same area, but we can see the difference in 2-bit and 16-bit. So what is the difference here? Now in the 2-bit we will see the image in only black and white. Okay, either it is black, either it is white. 4-bit we have four types of colors here, that is black, gray, white, again gray. Okay, now 8-bit it is having more number of clarification, again more differentiation we can do. Even though it is black and white differentiation, if you want to do all the features, then it has to give it more clarification for the differentiation, right? So here we have white, 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 white here, somewhat gray here, black here, gray here, more lighter gray than white. So more compared to this 4-bit, it will differentiate more finer. Now we go to 16-bit image, the clarification of the image will be more increased. So radiometric resolution of imaging system describes its ability and discriminate very slight differences in the energy. The finer the radiometric resolution of a sensor, the more sensitive it is to detecting small differences in the reflected or emitted energy. So 16-bit, more clarity, 2-bit, less clarity. So if the image is black and white, it's very hard to differentiate the images. So that's why if the radiometric resolution is having more 16-bit, that means 0 to 655 level or 0 to 8-bit maximum. 8-bit is enough to differentiate 0 to 256 or 0 to 255. Then we are able to identify or differentiate or discriminate the features in the image. So radiometric resolution of the imaging system describes its ability to discriminate very slight differences in the energy. Very slight differences. That means it is like a gray levels, white, light, color more lighter, then gray, light gray, dark gray, black color, dark black color, more darker. It shows a gray level of uh, features in the image for identification. So this is called radiometric. This before picture was black and white. Now if you see this radiometric resolution of uh, 8-bit and 4-bit of color image. So 8-bit shows more different colors. 4-bit shows less number of differentiation. For example, let us take as this portion area. So this portion you will see this watercolor itself, it is having more number of differentiation. Now here it has all totally green in color, light black is here. Now if you see there are more dark green, little light green, dark green or black, right? So based on this bit, now if you see this portion also it is discriminating more here, right? Now, so this is how we are able to identify the or discriminate or differentiate the feature if the radiometric resolution is higher. So this is high resolution, and this is low. So resolution should be maximum at least 8-bit it should be there so that we are able to discriminate the objects in the satellite images. Otherwise, if it is of 2-bit and 4-bit, it's very hard to differentiate the images. Okay, so next is temporal resolution. Temporal resolution specifies a revisiting frequency of the satellite sensor for a specific location. High temporal resolution means 24 hours, less than 24 hours to 3 days. So less than 24 hours to 3 days is higher temporal resolution. Temporal resolution means suppose this is the orbit and here is the satellite. So when the satellite starts on day 1, so while rotation, in how many days it will come back to its position. So this is its position. So in how many days it will rotate and come back to its position is called as temporal resolution. So this satellite is having temporal resolution of 24 days, okay, 24 hours, even 1 hour, okay, even 3 days, 6 days, depends on the higher resolution of the satellite image. Higher temporal resolution, it will come back in less days. More lower temporal resolution, it will take more days. So when you talk about 24 hours to 3 days, that means When the day one it starts, 24 hours means in a day it has to complete the entire orbit and come back to the same position. For example, so day one it has captured this area. Day one it has captured this area. Now, if it is 24 hours, that means first hour it will start in 24 hours. Again, it will capture the same area. So it will show the difference in 24 hours. What are the difference in this features in this objects? Now, medium temporal resolution will be 4 to 16 days. So 4 to 16 days means if day one it will start. So day one it will start means day four it will come back to its position. So day one it has captured this area. Now day four it will capture the same area. So temporal resolution means repetitive coverage. So first day how what it has captured, the fourth day also it will capture the same. So like this, if it captures for the 6 day, 3 days, 10 days, we are able to just see the difference in the cropping pattern. So this is very much helpful in the cropping pattern. Like if we grow a crop in first day, it will be in the growing stage. Second day, third day, or after 7 days, it will be in the more growing stage. It will be more bigger. After 1 month, it will be more bigger. So if we compare the images, we can just see the growing of the vegetation, growing of the crops, yield estimation we can do with the help of this temporal resolution. So temporal resolution is also helpful in the infrastructure development, like whichever area we choose for the construction areas. So it will show us which area is suitable for the construction and how much area is covered at that particular point of time, and how much area is left empty for the construction works. So if it is greater than 16 days, that means it is called as lower temporal resolution, right? So these are the four resolutions satellite is having. First one is spatial, second is spectral, third is radiometric, four is temporal. So these four resolutions are very important for a satellite sensor when it is capturing the information. These all resolutions should be must. So if the resolution is higher, then only we are able to use the data for the further uh, any type of projects, right? Now, spatial, spectral, radiometric resolution, which must be taken into consideration when engineers design a sensor. Okay, so if engineer wants to design a sensor, it has to they have to design the sensor in such a way that it should cover the spatial resolution, spectral resolution, radiometric resolution, and it should be uh, able to capture these all the resolutions with a higher level, right? For high spatial resolution, the sensor has to have a small instantaneous field of view. However, this reduces the amount of energy that can be detected as an area. The ground resolution cell within the IFOV becomes smaller. This leads to the reduced radiometric resolution, the ability to detect fine energy and differences. Now, temporal resolution, if we see the definition, to increase the amount of energy detected, thus the radiometric resolution, without reducing spatial resolution, we would have to broaden the wavelengths range detected for a particular channel or band. Unfortunately, this would reduce the spectral resolution of the sensor. Conversely, coarser spatial resolution would allow improved radiometric and spectral resolution. Thus, these three types of resolution must be balanced against the desired capabilities and objectives of the sensor, right? So temporal resolution is also very important part in the while designing the sensor, right? So basically these three are more important when the sensor is designed, that is spectral, radiometric and spatial. Okay, so I hope you understood about the resolutions. Like, we have four types of resolutions: spatial, spectral, radiometric and temporal. These are resolutions which are very important as sensor should have while capturing the information. Right. So these are the references for this content which we have discussed today. So like regularly, I just suggest you to just go through this book. M. Anji Reddy, Remote Sensing and GIS BS Publication, New Delhi. When you go with the fourth edition, it will be more better. Just go with the fourth edition, so you can just find out the more content about it. And we have these two links, NPTEL links, which you can go through to just find out the more content about the resolutions. And even though rest like fundamental of remote sensing, by George Joseph. You can just go through University Press Hyderabad, LRA Narayana. You can just go through these books for the resolutions and types of resolutions and more examples about the resolutions. You'll get to know more about if you go through this all, right? So that's all for today. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.